laser.
You guys ready? You ready for this? All right. So we're going to go over 4.31, okay? All right. So first of all, when we're looking at this problem, you guys are asked to design something that can get your two bottoms and tops, right? And so we have two different pressure maps that they give us for this problem. We have one that's at 0.2 atmospheres and one that's at 1 atmosphere, okay? So let's kind of get ourselves aligned on this. So we want our bottom stream to be here, right? We want it to be 2%, less than 2% of our volatile component, and we want our other one to be 98%, so basically like pure water, right? So we're doing a normal distillation column. So that seems pretty standard. We want to get to the top and bottom, all right? So unfortunately, today's been kind of an azeotrope day. I don't know if you've noticed that. We've been talking about them kind of a lot. So we have this azeotrope here, which is kind of annoying. It's about 0.8 on our 0.2 diagram. So that's interesting. So what does an azeotrope mean in terms of like actually getting up here to that azeotrope? Yeah, well.
It means you have to have an infinite amount of equilibrium stages just to get there, and then a couple more to get to the start of it.
Yeah, a couple more than any to get anywhere past that. So what does that remind you of? What else do you need infinite number of stages to get past? A pinch point, right? So that's one thing that I like to think about when I'm looking at that is that it's going to take me infinite stages to get that azeotrope. So I'm not going to be going up here and then getting past that on there. There's no way to draw that nicely so it works. It's not going to happen, okay? Good. So over here, let's look at our 1 atmosphere. We have our tops and bottoms again, and we have our azeotrope here. Okay, but wait a second. What's the different? What's with these azeotropes? They're different compositions, right? So that's pretty cool. It's pretty nice thing. So earlier we were talking, and we know we were doing that first presentation when we were talking about the azeotropes and how on the temperature map and on the pressure map they were the same. So why is that not the case for our two maps? We have two maps and we have the same stuff. We have water and our acetonitrile, right? So why aren't they the same on this? Does anyone know? What were the two types of maps we were comparing earlier? Pressure and temperature, right? So what type of maps are we comparing now? Two pressure maps. So because we're changing the pressure here is what's causing the azeotrope to change. So that's one thing to note, and that's why we have two different azeotropes. So it varies with our system pressure. So what do we do when we're approaching this problem? All right, so here's our thing. So what did you guys do when you first started doing this then? What did you guys want to get? Anything? You did nothing. You looked at it like that, sadly. No? Well, what's up?
Well, like halfway through, we changed the pressure to skip over
the azeotrope. So you started with one of these maps. Which one do you want to start with?
0.2.
We want these to be our bottoms, right? So can we start with 0.2? Does that sound okay with everyone? Because this is the bigger one for this bottoms area. So first of all, so what we're going to do is we're going to draw ourselves some operating lines. So I know that there was a lot of like hubbub about where should we draw our operating lines, should we have operating lines, etc., etc., etc. So I saw a lot of people who drew this as our operating line. Okay? So why need operating lines other than this x equals y line? What does our operating line signify? What does it mean? What is the slope of our operating line equal to? Our liquid over our vapor, right? So what is this? What's the slope of this line? 1. So that means that our liquid composition and our vapor composition in our stream are the same, right? So that's kind of inconvenient because we want to take stuff out of our column. So if we're operating here, we're not actually taking things out of our column. So that's not good. So we definitely need operating lines if we want to take stuff off the top and out the bottom of our column, okay? So I put these operating lines here. Another thing we were talking about a lot was the feed composition and where that feed is. So where is our feed in this case? Dan?
It said that the feed was like 20% acetonitrile.
Yeah, so it's like 20%. So it's in here. So when we actually like go to draw stages on here, the way that we're going to deal with feed in this class, which isn't how you're always going to deal with it for this class, is basically we're going to say that if we go up from 20%, if our feed stage, if we have a stage that falls within this 20% kind of range, so if it was pure vapor at 20%, we'd be here, right? And we could come across this way. And if it was pure liquid at 20%, we would go up this way, right? So basically we're going to take this equilibrium line and kind of go in between here. And if we have a feed stage that touches in between there, then we're going to call that good, okay? So for this class, it's kind of what you need to deal with. If you're not given a specific like feed, if you're given a feed composition, just make sure that it falls in this range of 20 to 20, okay? Does that make sense to everyone? So we just kind of made our operating lines, we put these on there. It's not like a huge deal about what exactly you did. You're not designing the column. We're looking for a process, not a column, okay? You'll design columns later. It'll be so fun, okay? All right, so now what do we have here? We have our 3 stages required in our column, and we have this output, right? We have an output of around 76-ish, okay? So maybe a little bit lower, like 75. All right, so we have these 3 stages in our column. Okay. Oh, 77. Wow. Apparently I'm optimistic. Okay. So we have our input, our 2 outputs out of this column, and we're operating at 0.2 atmospheres. So what did you guys do from here?
Take 77%, go to the other atmosphere.
Yeah, so basically we're going to take this, and we want to go up there, but we can't. So what if we put this other line, and we see where this other one is, and see where we are there? Well, that's actually really nice, kind of convenient. So we're at this, we want this distillate to be up there, right? So let's go ahead and operate at 1 atmosphere. Switch over, we're now on this map. We still have that same output coming out of our other column, right? Just because we're changing its pressure doesn't mean we're changing its composition, its overall composition. So we're going to draw some feed stages up in this corner. And we're going to follow the same kind of formula as we did for the last column and draw ourselves some stages and put it up there. All right, good. So if I were to start numbering these stages, and I was to number from the bottom of the column to the top of the column, where would I start numbering? Where's the bottom of the column in this case? Does anyone know? Richard, you're looking at me like... any idea? It's actually, the bottom of my column is actually up here. And you know why that is? Because if I take this map and I flip it around, when we're in this area, this looks more like our normal equilibrium line, right? We generally deal with this here, and then we have our equilibrium curve being above our y equals 1, our y equals x, right? And the reason we do that is because we put our most volatile component as our axes on these graphs. But when we switch into this azeotropic region, is that correct? Past the azeotrope. When we go past the azeotrope, what is the most volatile component in the system actually changes. So what's the most volatile component in our system now? In this region? Water, right. So this is basically, I mean, if you did simple math, you would know that this was y, one minus the other one and one minus that one. But maybe you didn't think about it like that. You could flip it over, and basically you're now looking at a y water and x water diagram. So now this looks a lot more comfortable, a lot more familiar. We can step off those stages, and we can see that the bottoms here are above 98% here, but less than 2% water. Does that make sense? Because we're just dealing with the reverse. We're now dealing with water instead of our acidic child. Okay? Then we have our other composition there. So now we know what's coming out of the bottom and the top of that second column. And that second column is operating at 1 atmosphere. So we have our 2 streams that we wanted. Looks pretty nifty. So what do you guys think? Look good? Yeah.
Recycle stream 4.
Recycle. Recycle. So we can always recycle this. We can put it back in here. And we're going to change our feed composition a little bit, right, when we recycle it back in there. But based on our column that we drew for A, this new composition, which is based on the flow rate, is going to still be somewhere between 70% and 80%. Or, well, I guess it's going to change, but it's still going to be in that area, right? We'll be okay. So when we're dealing with something like this, you're not like being asked to get the flow rates of streams. We know that that would be complicated. As long long as it still works within the feed stream area, you'll be fine. Okay? Questions? Concerns? Yeah.
Could you just add them back into the column at a different feed, or would that not be good?
Could you add it to like the same column and a different feed? You can have more than one feed stage in the column. There's no problem with that. So yeah, if you decided, you know, I want to add it when it's closer to this actual composition, you could definitely go to your column and do that. No problem. Okay?
And that would be better, because now you're taking something that's very pure acetonitrile, mixing it with 20%, put it in a stage where it matches that composition. You don't have to undo what you've already done.
Good. All right. Other questions?